Let's talk about decoding. Last time with encoders, we talked about we could take some arbitrary outside information and encode it into something that a computer could store, which are just series of ones and zeros. And at the time we did, kind of a decimal to binary representation, but we don't have to. As long as you know what you use to encode it, you can encode data any way that you want. So to prove that, we're going to assume that we had a keyboard and we had an R, and we want to encode that data as a 001. Okay? And then we had a button that had an O on it. And we want to encode that data as 010. So that's binary 2 if you're talking about decimal to binary conversion. But when we encode, as long as we know how we encode it, we can decode it again to get the information back out. All right, let's say we had a button, had a B on it. We want to encode that as 011. Okay. So we've got 3 buttons out there, the most important buttons. We've got a little keyboard, and all you can type is really Orb and Rob. Robo. But, the important stuff you can type. All right, so we've got 3 buttons out there. And whenever somebody pushes an R, we want to store a 001. Whenever somebody pushes an O, we want to store a 010. And whenever we store a B, we want to store a 011. Okay, we could easily make an encoder to do that. Now, I want to get the information back. And as long as I know what I use to encode it, I can use that same kind of thing that we did last time to decode it. Okay, so we've got something called a 7-segment display. Okay, and it looks like an 8, but it's got 7 segments. One, 2, 3, 4, 5, 6, and 7. Okay. And so let's say that when I encoded the R, instead of just wanting a little light to shine to represent R whenever I'm decoding it, I want something to kind of visually represent that R. Okay. I want it to be human understandable. Okay. And so a 7-segment decoder or a 7-segment display, is really good. We can make 0 through 9, A through F, a bunch of other, things if we're, creative about it. So what I'd like to do is I'd like to take the 7-segment display and use it to output that R, O, and B. Okay. So let's say that I want to encode or decode an R. I might have G and E shine. Okay. So when I decode it, I want the segments G and E to show. Okay. Now for an O, I might want G, C, D, and E. Okay. So all I've got to do is make sure that those LEDs are shining when I'm decoding a 010. All right, so this one would be GE, and this one would be GC, D, and E. Okay. And then for a 011, I want F, G, C, D, and E. Okay. So let's, for ease of, let me jump back on that. All right, so decode it. We're going to be getting a binary chunk of data, and we're going to want these LEDs to turn on in that order. Okay, so let's think about how we'll do that. All right. So we just want a G, E. And this is why I want you to be careful when you see a chunk of binary data. When you see a 0, 1, 0, you automatically assume that it represents a 2. And when we're doing decimal to binary conversion, yeah, it can. But it's just a collection of ones and zeros, okay? It takes on meaning by how we encode that data and by decoding it later, okay? So a 0, 1, 0 in this context is not a 2. It's going to represent from now on an O, okay? And then we're going to say 0, 1, 1, which would look at, and hopefully by now with your binary learning, and in chapter 2 you would you'd want to see a 3 there, okay, just in your mind. But today it represents a B, okay, so I push that B button, and I should see something recognizable as a B. Okay. Now, let's talk about simplification a little bit. All right. So with nothing pressed, we don't want anything out. Okay. Now, if we had more than 4 chunks of data that we needed to represent uniquely, would have to use 3 bits. Like 3 bits would give us 8 different combinations that we could do. We've only got really 3 letters that we're trying to represent right now. 3 letters we can represent with just 2 bits. So one of the things that you should see right now is that most significant bit right here we can kind of get rid of. We can do this with 2 bits. Okay? So we're going to say 0, 0, nothing. 0, 1, we're going to output what we say is an R. 1, 0, we're going to output what we say an O. And 1, 1, we're going to output a B. Okay. So let's look at what the circuit should look like. We can draw up a truth table. We'll say A, B. We got 0, 0, 0, 1, 1, 0, 1, 1. And then we don't have to worry about the A. The A is never coming on for us. We don't have to worry about the B. The B is never coming on for us. But we do have F, well, let's start C, D, E, F, and G. Okay? And let's see what those are going to look like. We can draw out our truth table. Oh man, my artistic acumen is suffering this morning. All right, so let's flip that and let's see when C is on. Okay, so C is an output. All it cares about is whenever it's on. And that's when we've got a 1, 0 and a 1, 1. All right, so we find when C is on, and it's going to be a 1, 0 and a 1, 1. When is D on? All right, so we'll 0, 0 that. D is on at the same time as C. When is E on? It's pretty much on anytime we push a button. Okay. What about F? It's only on 1, 1. Okay. What about G? G's on all the time. Okay. Now, before we get really deep into, simplification with, Karnoff maps and things like that, let's make our life a little bit easier. Okay. Before we do anything, let's just see if we can make our life easier. Okay. So, F to me looks like an AND gate. So when, A and B are on, it's an AND gate. E and G look like an OR gate. So, when we get down to simplification, this is going to, start kind of popping out at you. And then C and D don't really have a set gate for that, but they look like they're going to have the same thing going on. Okay, so we're going to use that to our advantage. Okay, so instead of doing C and D over and over again, we're going to have, C and D tied to the same thing. So we can just figure out the logic for that, and we're good. E and G, if we tie those together, we're going to be good. E and G come on at the same time, right? And then F, we're going to have to be special with F, okay? So that's going to save us a lot of gates already by recognizing that the C terminal and the D terminal coming on at the same time. We can use the same logic to drive both of them. E and G coming on at the same time. We can use the same logic to drive both of them. F is by itself, but we've saved some time already just by taking a bigger picture of it. All right. So let's get to work on C and D. When is C and D true? When it's 1, 0 and 1, 1. Okay. So we can just take those combinations and OR them together. If A is 1 and B is 0, or if A is 1 and B is 1. All right, so for C and D, we can go in and we could take that A and B. And if, let's put B down on the bottom. And if A is 1, so we don't have to invert it, and B is 0, so we do have to invert it. Or if both of them are A, so an AND gate would happen or would make 1 if both of those are 1, so we don't need an inverter on those. And then we ORed that. All right, so now we've got the logic for C and D. E and G. We could say if A is not 1 and B is 1, or if A is 1 and B is 0. All right. Or if A and B are 1. Now, when we go back to Boolean algebra, it tells us if you or the complement of something, you're always going to get 1. Okay? Like, because if you complement something, you're always going to get a 1 from one or the other. If it's 1, you've already got something triggering or. If you've got a 0 there, then you complement it, so you invert it. That's going to give you a 1 on the other side of that OR gate. That's a kind of complicated way of making you look at something like E and G, and the circuit that I just built would do it, but we don't really need all of those gates. We can simplify it down to nothing but an OR gate. And if you look at how the how E and G actually look, it screams an OR gate. Okay, and that's a kind of force for the tree's big picture that I need you to be starting to get a feel for. All of those Boolean algebra rules get down to stuff that, like, if you kind of think about it, makes sense. And so take that, prove it with your Boolean algebra that this could be worked out to nothing but an OR gate. Okay? So to save time, I'm not going to, waste gates. All right? I've got, I've got a gate that is complementing the A, and then it's complementing the B, and it's doing the other, the non-complemented for the other input. I don't want you just to trust me. I want you to go prove it. Okay? So, I might get you to make this circuit and make an OR gate, but for today, E and G going to be A or B. All right, when is F? All right, so F is on if A is 1 and B is 1, and that's it. So F is going to be A ANDed with B. Okay. Now, that combination of things might get harder to see, or that pattern might get harder to see as you add more inputs or more outputs. But that's what the Boolean algebra is for. Like, that's to make it so that even if it's not apparent on the surface, that you are able to get it down to this. So next week we're going to do a bunch of simplification. Okay? I just want you to look at it with fresh new eyes and be like, oh, wow. Because I could put C as being A not ANDed with B not, A not ANDed with B, A ANDed with B not, or AB ANDed together. And that'd be a whole lot of gates that we could simplify down to nothing but an AND gate. Okay? So what I want you to do is pull up deeds. We're going to build this joker. And, stroke my ego while doing it. we've got something new here. If you go under outputs, you can get a 7-segment display. And like if you get a decoded one, you put in a binary you put in binary data, and it's going to put out the numeric representation of that data from a binary to decimal conversion. We could do that. We could go and code 0 through F and then decode it so that it would show a 0, a 1, a 2, a 3. But I don't want you to think that this 7-segment display is anything magical. It's a 0 because we agree that it's a 0. Okay. So put that 7-segment display unencoded in there. And we've got our 8 inputs. All right. DP is 4 decimal point. All right. So for our first one, we can go back and look. We need to do an A ANDed with the B naught, or A ANDed with B. All right, so let's go ahead and drop 2 input AND gates. Let's go ahead and do our OR. Okay. Let's go ahead and do our NOT for our B naught. Okay. Now let's take our do Control W, Command W. That's not working. Why aren't you working? Let's take that A out. Let's connect our inverter to our AND gate. Let's take B out. Let's put it a little short so that we can say A is on the left and B is on the right. All right, and then we're going to take our B that needs to go into here, and we're going to take our A needs to go into here. Let's go ahead and put our switches in. So this is A. This one's going to be B. There's still a lag on this, so it's making my wiring harder than it should be. Alright, so we've already said that works for C and D. So we're going to take C, connect it with D, and we're going to come out. Booyah. Alright. Then for E and G, we just said that's an OR gate. So let's take that OR. And let's tie it to A. Word with B. And we said that was E and G. I'll just go to, let's move up a little bit, E. And then G. And then we said that F was just A and B ANDed together. I did this on purpose. I want you to start getting an intuitive feel for what we're doing when we're simplifying circuits. Okay? Like, it's a good way of looking at a mess and kind of finding a easier solution for it. Okay? We're going to take A, which we'll just dump it off of this A bus. We'll take that. Alright, so everything being as it should, we go and play it. We're going to call this Rob Decoder. Alright, so we've got some little red things representing that they don't have anything on there, so they're floating, and it doesn't know what those should be. They don't need to be a 0, they don't need to be a 1, so they're nondescript. Doesn't really matter. Alright, so ignore those. On 0, 0 we have nothing. On 0, 1 or 0, 1, we should have an R, right? There we go. B is the least significant bit. So we've got 0, 1, it gives us an R. 1, 0, it gives us a B. And then 1, 1, it gives us 1, 0, it gives us an O. And 1, 1, it gives us a B. Alright, so that's decoding. And that should show you that the binary data could be any of infinite things. Okay? It if we're smart about it, we need to have a good reasoning behind how we encode data. Standards. If we don't have standards, then all it is a big old chunk of secret information. It's just like during war. Like you've got encoding. You're going to change something into a different form, and hopefully people won't be able to see what the original form was unless you want them to. Okay? So this is a terrible encoding and decoding scheme, because why would I waste a bunch of gates just to show an R, or just to show an O, or just to show a B, unless I'm super conceited, right? But I wanted to show that there wasn't any black magic to it. You see a 7-segment decoder, showing 0, 1, 2, 3, and you think that computer understands that that's representing a 3. It doesn't. Like, it just knows that when I get this combination, I need to put this combination out. Okay, so I want you to read through the decoder aspect, and I kind of want you to take your time and start kind of trying to internalize it. We're available all the time, so there's a few people who come in and they get help. And if you're feeling lost, come in and I'll sit down with a piece of paper and we'll figure it out together. All right, so this is the deeds part that I'm going to want you to show, but hope it opens your mind up to something.